This program is brought to you by Stanford University. Please visit us at stanford.edu.
What are we going to do today? I thought I would perhaps teach you a little bit about cosmology and the extension, well, just a tiny bit about the extension from special relativity to general relativity, just a little bit, and then how general relativity is applied in cosmology, what real space-time is like, as opposed to the flat, featureless, boring space-time of special relativity. The space-time of general relativity is active, it's curved, it responds to things, and allows all kinds of wonderful things to happen, such as the evolution of the universe, the Big Bang, and so forth. So I thought we would just discuss that a little bit, spend a couple of hours seeing if we can encapsulate and summarize basic, very, very basic cosmology. If there are no objections to that and there are no questions about previous things, I'll begin. Yeah.
Quick, I hope, question. Last time we derived Maxwell's equation, I want to be sure I understand the constraints and conditions. All we assumed was that there are some attributes of electric and magnetic fields that are Lorentz invariant. Is that correct?
Yeah, pretty much. Yep. Well, no, but there's much that we assumed. Yes, we assumed there were some electric and magnetic fields. We assumed that the equations for electric and magnetic fields are Lorentz invariant, of course, and that went a long way to deriving the structure of Maxwell's equations. But we also assumed that the equations were linear. In other words, every single term in the equations involves at most one power of the electric and magnetic fields, that there were no terms with electric field times derivative of the magnetic field and so forth. That would be said, we would say that that means that the field theory is linear. I'll tell you what that means in a moment more specifically. Well, it means what I said, that the fields come in only to the first power. We also assumed that Maxwell's equations did not have higher derivatives in them, that there were no terms in the Maxwell's equations with 16th derivative of the electric field or something. Those were assumptions. But with those assumptions, Lorentz invariance and the assumption that the electric and magnetic field fit into a single entity that transforms coherently is enough to prove Maxwell's equations. The statement that a theory is linear, what that means is, let's suppose it's a theory for some field or some coordinate or some degree of freedom. Let's just call it phi. It could be a field. It could just be the position of a harmonic oscillator, any quantity which does something interesting. You have some equations for it, and there are solutions. And the solutions will be of the form phi of x and t. Well, if it's a field, it'll be a phi of x and t, which is some definite function. I don't know what to call it, except let's call it a of x and t. That's a solution. If the equations for a theory are linear, then, among other things, that means that if you multiply a solution by any number, it's also a solution. So if you have a wave, you can multiply that wave by 125 or anything else, and that will just magnify it or amplify it, make the waveform higher and deeper without changing its shape other than to stretch it and to make it stronger, that's still a solution. Right? So doubling the amplitude of a wave, tripling the amplitude of a wave, or multiplying it by a very small constant, any number, is also a solution of the equations. Right? That's one statement. The more interesting statement is that if you have two solutions, a of x and another solution b of x and t, then the sum of the two of them is also a solution. So what that means is that if you have two different waveforms, for example, let's say a waveform of looks like this, another one which, oh, I don't know, has a higher frequency, smaller wavelength, looks like this. If you add them up, you'll get a wave which looks like, a little hard to draw, but let's draw it. One wave superimposed on the other, just add them, and that's also a solution. So you can add waves. One implication of that, for example, is if you have a wave moving along, it's coming in from the left, and another one coming in from the right, if you didn't have the left wave, the right wave would simply move to the right wave would move to the left and eventually just move off. The left wave would move to the right and also just move off. The sum of the solutions after a long time would just be two waves moving past each other. Linear equations have that feature that waves which are propagating, let's say, toward each other, will just pass through each other without scattering, without getting stuck, without anything happen. They're completely transparent to each other. They don't affect each other because the sum of the solutions is still a solution. So that's the character, that's one of the features of Maxwell's equations, linearity. As I said, what that says is that two electromagnetic waves will just pass through each other without doing anything at all. Now, electromagnetic waves can talk to each other, so to speak. They can interact with each other, but they interact with each other by virtue of interacting with electric charges. And electric charge, which happens to be present, maybe a whole bunch of electric charges, the whole bunch of electric charges will be excited and vibrated and tend to have forces on them because of the electromagnetic fields moving through. And so a field moving through a bunch of electric charges will start them oscillating and create new waves. Those new waves, which were not present in the absence of the charges, cannot be thought of as in any sense the sum of the original two waves. It's just newly created waves. And so there are nonlinear effects in electrodynamics, but only because electromagnetic waves can affect charges, and charges can affect electromagnetic waves, and the net effect it can sometimes be for one electric wave to affect another electric wave. That's the classical theory of electromagnetism. No direct effect of one electromagnetic wave on another. Now you could imagine, let's write down some linear equation. Anyway, a harmonic oscillator. The harmonic oscillator, the equation is d second x by dt squared. This is the acceleration times the mass is equal to the force, which is minus some spring constant times x. Suppose I have a solution of this equation. And now I take another solution of the equation. I'll just write it down again. Instead of calling it, I'll call this x1 and x1. Another solution, the x2 by dt squared, equals minus kx2. These correspond to two different solutions of the same equation. If I add the two equations, I just get that m times the second derivative of x1 plus x2 is just equal to minus k times x1 plus x2. So you see directly from the form of the equation that the sum of two solutions is another solution. But suppose I change the equation. Suppose I put here another term, let's call it p, times x1 squared plus something else, plus p x2 squared. These are both solutions of the same equation, but the equation is now nonlinear. Nonlinear means it has quadratic things in the fields, x squared. If you add these equations, what you'll get, m times d second x1 plus x2 by dt squared equals minus k times x1 plus x2, but the last term here, p, is not x1 plus x2 squared. It is not x1. I've written it, but it's not true. Px1 squared plus px2 squared is not p times the sum of x1 and x2 squared. So x1 plus x2 is not a solution of the equation when you have something quadratic there. It simply just doesn't solve the original equation, even though x1 and x2 do. There's no doubt that you could have added things to Maxwell's equations which are nonlinear. Nonlinear means that it would contain on the right-hand side of the equations things quadratic in the electric field, things quadratic in the magnetic field, analogs of this here, which if they existed in Maxwell's equations would cause electromagnetic waves not to pass through each other, not to be transparent to each other, but one electromagnetic wave would affect the other and cause it to scatter, cause it to do other things. So you asked me whether you can derive Maxwell's equations from the principle of relativity alone. I think that's roughly what you asked. The answer is no. No, there's much more in it, some of it coming from experimental physics, such as the fact that electromagnetic waves do freely pass through each other. But you add together a few assumptions, linear, not too many derivatives in the equations, and that's enough. But no, you can't derive, I don't know any basic law of physics that you can derive just from relativity alone without some input of a physical, experimental type. Symmetries constrain theories, but they don't determine them as a rule. Okay, any other question? Good. All right, so let's move on to, first of all, a little bit about general relativity, very little, but then on to cosmology, what real space-time is really like. Expanding space-time, inflating space-time, which cannot be described by special theory of relativity. It requires a more general structure called the general theory. All right, the special theory of relativity can be summarized by a very simple idea that there's a geometry of space-time, and that geometry is determined by knowing the distance between every pair of neighboring space-time points. This is a fact about geometry in general, about Riemannian geometry in general, that if you know the distance between every pair of neighboring space-time points, that in principle you can reconstruct the entire geometry of space. I'll give you an example in a few minutes, but of a non-trivial geometry. But you represent then the small interval between 2 points by a coordinate, a set of coordinates. We can call them x mu, where as usual, mu runs from 0 to 3, and another point, x mu plus dx mu, where this little interval is called dx mu. What's the distance between those 2 points? The distance between those 2 points, of course, it is whatever it is. It's, what is it? It's a certain space-time interval there. But how do you represent it in terms of the coordinates of those points? In general relativity, we wrote that the distance between those 2 points, ds squared, is equal to dt squared minus dx squared minus dy squared minus dz squared, which we can also write as dx mu dx mu. And another way that we wrote it was eta mu nu dx mu dx nu, where eta was just a matrix. It was a very simple matrix. Oh, did we call this tau, proper time? Maybe we called it tau, proper time, where eta was just the matrix 1, minus 1, minus 1, minus 1, zeros everywhere else. Those were three ways that we wrote the space-time interval between neighboring points. Now, one statement of the general theory of the special theory of relativity, the special theory of relativity, is that the tau squared should be taken to be an invariant of the geometry. In other words, all observers, generally they will not agree on what dx is. If we rotate coordinates or Lorentz transform coordinates, they'll disagree about the components of dx, but what they will agree about is the proper time between the 2 points. So the proper time is an invariant. That's one initial starting point for a sort of axiomatic description of special theory of relativity. The second statement, which is not an axiom, it's a theorem, is that the transformations that you can do on x, y, z, and t, which preserve the form of the interval, are Lorentz transformations. If we look at Lorentz transformations and rotations and so forth, the interval in terms of primed coordinates has exactly the same form as the interval in terms of the unprimed coordinates. So that's a statement of symmetry, that the basic proper time can be expressed in all Lorentz frames by the same basic formula. And then the final statement is that having found what the symmetry of the interval is, having found out what the symmetry of the, what family of coordinates always gives the same answer here for the interval, then the rule is all laws of physics are identical in those different frames of reference which are related by Lorentz transformations. Now, of course, it is not true that every set of coordinates that you could think of, the interval is expressed in the same way. Let me give you an example just from ordinary space, not space-time, but space. If I take coordinates x and y, which are the usual kind of, x and y, the usual kind of Cartesian coordinates, then yes, the separation between 2 points is just dx squared plus dy squared. If I rotate the coordinates to x prime and y prime by a standard rotation of coordinates, then the same interval is dx prime squared plus dy prime squared. But what if I do something dumb, like use a coordinate mesh where x and y are not measured in the same units. X is measured in inches and y is measured in meters. I have a point xy and a point x plus dx and y plus dy. What is the distance between those 2 points? It is not dx squared plus dy squared. Why not? Because you're measuring the interval in different units. In particular, supposing I wanted the distance in inches. Let's see. Let me use centimeters here. Centimeters and meters. Centimeters and meters. I don't like factors of 12 and factors of 144. Factors of 10 are easier. All right. Supposing I want the distance between neighboring points, but I want to measure it in centimeters. In centimeters. This is x and this is y. What is the distance between 2 points? It is not dx squared plus dy squared, but it's dx squared plus dy divided by 100 squared. Why over 100? Well, it's obvious that if you use the same unit for y as for x, and you're measuring things in centimeters, then it would be dx squared plus dy squared. But if I use meters for the vertical axis here, and I want to get back to centimeters, I better divide the y component of vectors by 100. All right, so we could rewrite this then. It's dx squared plus 1 over 100 squared, 1 over 10,000 dy squared. So if I do something stupid like use awkward coordinates in where x and y are not measured in the same units, then my expression for distance is going to have a form which will contain some funny numbers in it, like 1 over 10,000 here. In particular, it won't be the nice symmetric dx squared plus dy squared. I go a little further. Supposing I don't use orthogonal coordinates. Supposing I decide to choose coordinates in the following way. I choose coordinate axes which look like that. And now my rule is going to be the coordinates of a point are gotten by moving along the x-axis, not to the point where you drop a perpendicular, but where you draw a line parallel to the y-axis. Likewise, the y-coordinate, so this would be the x-coordinate and this would be the y-coordinate. Then the distance between 2 points, you don't have the standard Pythagorean theorem anymore. We have triangles now. Here's x, here's y. This is not a right triangle. So the hypotenuse is not a hypotenuse. It's just a third side of a triangle. The length of this is definitely not dx squared plus dy squared, even if we use the same units on the x and y axis. It's just not true. What is it? What is it? Well, I won't write down precisely what the formula is, but it will always be of the form of some coefficient dx squared plus another coefficient dy squared. Let me not call it d. Let's call it a, b, and c. A, some number b, dy squared. But then what's new about coordinate systems which have angles in them like this, which are not rectangular, which are not perpendicular, is that there are additional terms, we can call them c, times dx dy. Products of different coordinates. That's what happens if you have coordinate systems which are not orthogonal, which are not the orthogonal coordinates, off-diagonal elements like that. You can also write this in another way. You can write it c over 2 times dx dy plus c over 2 times dy dx. And so you have a whole bunch of coefficients. We could give these coefficients names. We could call this 1, 1 for the fact that it multiplies dx squared. We could call this 2, 2. Well, why are we giving them different names? We could just call it A22 or AYY. This one we could call AXY. And this one we could call AYX. Notice that AXY and AYX are exactly the same thing. I simply took the coefficient of dx dy and split it between two terms, one which is dx dy and the other which is dy dx, just to symmetrize it, just to make it nice and symmetric. Finally, I could display these coefficients A as a matrix. A11, A1, well, XY, 1, 2, 2, 1. A12, A21, A22. Just display them as a metric, as a matrix. In fact, the matrix is called the metric. And this metric completely encapsulates what the distance between neighboring pairs of points are in terms of 4 coefficients laid out as a matrix. This matrix is called the metric. Right? Now, if we're dealing with ordinary space of the blackboard, flat space, uniform space, everywhere the same, and we choose our coordinates, let's say at an angle, but we choose them by marking off distances which are equal along the x-axis, distances which are equal all along the y-axis. then these coefficients will just be constants. They'll be constants because they'll be constants all over the plane here. Again, if we did something foolish, like decide to use coordinates which lump up over here and have a very different spacing, in other words, where the coordinate spacing by the horizontal axis here is x, this is x equals 1, this is x equals 2, this is x equals 3, 4, 5, 6. We've made the coordinate mesh very non-uniform. Then it's completely obvious that these a's will not be constants, because depending on where you are, the coordinate mesh might be finer or coarser and so forth. And the result of that will be that in general, if you use arbitrary coordinates, crazy coordinates which are curved and all kinds of complexity, where the spacing between coordinates is non-uniform, then the general rule will be these coefficients will be functions of position. What functions of position? Not any functions of position if we're talking about the flat plane, but a fairly wide class of functions can describe the interval between 2 points in what I could call crazy coordinates, coordinates which have curved axes and which are non-uniform. But nevertheless, the basic geometry of the blackboard is determined by knowing the distance between every pair of neighboring points, where the points could be described by coordinates x and y. All right, the same thing is true in special relativity, that if you use the right kind of coordinates, that means coordinates obtained by Lorentz transformation from each other, then the space-time interval between 2 points is always of the same type, always of the same form. If you use some cattywampus coordinates which are curved, which nobody can prevent you from doing, I mean, we can always use any coordinates we like, then the general formula will be very, very similar to what we've written here. And I'm going to write it down. The general formula in any coordinates of exactly the same quantity would be d tau squared is some set of coefficients, and they're usually called g mu nu, of position. They'll generally be functions of position, and then you'll have the x mu dx nu. Just in case it was not obvious, this can also be written as aij dxi dxj, summed over I and j. So this is a very, very general way of writing the space-time interval between an arbitrary pair of points. And if you know what g mu nu is, then you know the space-time geometry completely. If you know the space-time geometry completely, that does not determine what g mu nu is. Why not? Because you could always go and change coordinates. You could always go and change the coordinates in space-time in some peculiar way and change what g mu nu is. So g mu nu determines the space-time, but the geometric properties of it, the distance between neighboring points and so forth, but not the other way. The geometry doesn't completely determine what g mu nu is. Okay, any questions about the symbols on the blackboard thus far? This is just a more general way of writing the spatial and temporal relationship between points. And of course, there are many possibilities for the choice of the functions g mu nu of x. Okay. Now, let's go back to ordinary space. But imagine a space which is not as flat as the blackboard, which is curved. Let me first tell you what curved doesn't mean. If I take this piece of paper here and stretch it out nice and flat on the surface here, will all agree that that piece of paper is flat. Relations between points, for example, the fact that, that triangles have angles which add up to 180 degrees and so forth, that's all determined by knowing the relationship between distances of neighboring points. Now I take this piece of paper and I bend it nice and gently into a, let's say, into a cylinder. Or let's not close it up. Let's just bend it in some way like that. I haven't stretched it. I have not stretched it. I've only bent it. Okay? That is not what's called curved. In fact, most explicitly, if you take a flat piece of paper and deform it without anywhere stretching it, you don't change the distance between any pair of neighboring points. The distance along the piece of paper, the distance being calculated moving by a little tiny insect moving along the piece of paper, would not change. Why not? Because I haven't stretched anything. In fact, a creature that lives on this piece of paper, that can't look off the paper, can't look on one side, can't look on the other side, only is aware of motion within the piece of paper, would not detect the fact that we bent the piece of paper. Every pair of points would have exactly the same distance as it had before, and mathematicians do not refer to this process as curving of space. Curving of a space is what happens when you cannot flatten it out on the surface here without deforming it, without stretching it, without changing the distance between neighboring points. So for example, if I took a hemisphere of rubber, not a hemisphere, not a solid hemisphere of rubber, a surface, like the surface of a balloon, and I tried to, let's cut the balloon in half so it's only a hemisphere, and I tried to put it down on the table here without stretching it, obviously I can't do it. I would have to take the boundary of the semicircular, of the circular boundary of the piece of the balloon that I captured, and I'd have to stretch it. I'd probably have to squeeze the center of it to push it down onto the plane. And that distinction between bending, we'll call it, and curvature, real curvature. Curvature is that which is there when you cannot deform something to make it flat without stretching it. That's called curvature. All right? Again, if I take some curved, let me give you an example. A sphere is a very good example of the surface of a sphere is a very good example of a curved space. You cannot flatten a sphere onto a plane without stretching or deforming it, and that's of course known to you all that, that's the reason that you can't draw maps that don't stretch Greenland and make it huge, and Greenland on a Mercator projection looks as big as Africa. It's only about 1/10 the size in area, and it's because the sphere is curved, it's fundamentally curved. Now, the space-time or the spatial distances, let's go back to space distances of a sphere. Let's take a sphere. We can put coordinates on a sphere, such as the coordinates on the surface of the Earth, longitude and latitude. They're angles. One can be called theta. The other can be called phi, polar and azimuthal angles. You can also express the distance between neighboring points on the sphere in terms of little differential expressions like this. The main difference, or the fact is, no way of coordinatizing the sphere will allow the components of the metric to be constant in space. They will necessarily vary from point to point in space. That's the test. It's not an easy test to implement in general. There's a better test, but the right test for whether a surface is curved or not is whether you can find coordinates in it which make the coefficients of the metric constant in space. If they're constant in space, it means at worst your coordinate axes are tilted relative to each other, but nevertheless the space is flat. If it's impossible to find coordinates where you can flatten out, where you can represent the metric as being constant, then you have a fundamentally curved surface that you cannot flatten out. So curvature is an obstruction to flattening out a surface and making the metric a constant matrix. That's the notion of curvature. In practice, the examples we're going to do are very simple. Let me give you a nice example of a funny set of coordinates that you can use on the plane. Polar coordinates. You all know what polar coordinates are, I hope. You represent points by angles theta and radial distance r. Okay. Supposing I want to talk about the distance of, well, let's see. Yeah. Let's take a interval here. This is some dr and some d theta. What is the distance between this point and this point? I'm going to write it down. I'm going to write down the answer for you. You can check it yourself. The answer is very simple. It's dr squared plus r squared d theta squared. Why is it r squared d theta squared? D theta now is just the change in angle between these 2 points. All right. You draw yourself a little right triangle here, one side of which is dr, but the other side is not d theta. For a given d theta, the further out you move, the bigger the side of that triangle. The side of this triangle here is not d theta, it's r d theta. So Pythagoras' theorem tells you that this is dr squared plus r squared d theta squared. Here's an example where the coefficients of the metric are not constant.
Isn't it r sine d theta?
No,
Or cosine?
it's r squared d theta squared. You're thinking about a sphere.
Theta and radians, so the axis.
Theta is in radians. Yeah.
Oh, okay.
Theta is in radians. No, there's no sign there. So, is that what you asked me, if it's a sign?
It seems like for small things, it would reduce to d theta, but for
No. No matter how small d theta is, if you go far away, the distance grows. So the distance along the d theta side here is proportional to r. Yeah. Yeah, r, that's right. Arc length is always r d theta. And so now we have a metric which we can display in the matrix form, 1 over here, the r squared over here, multiplying d theta squared, 0, 0. So here's a simple example of a coordinate system where the flat blackboard is displayed with a metric which is not constant everywhere. Okay? But what I can do is revert back to x and y coordinates. X equals r cosine theta, y equals r sine theta. Rewrite this expression, and lo and behold, it just becomes dx squared plus dy squared. In which case, the metric in these coordinates is just good old 1, 1, 0, 0. So the flat plane, or the fact that this is a flat plane, may not be so obvious when it's displayed in this peculiar way here, not the x squared plus dy squared, but r squared, the r squared d theta squared. But nevertheless, the fact that you can find coordinates to flatten it out means that the blackboard is flat, even though you've displayed it in some curvilinear, funny coordinate frame. On the other hand, if you would take a sphere, let's work out the metric on a sphere. All right, we have one coordinate, which I guess is called polar angle, and it's the angular distance along the sphere. Let's take some arbitrary point over here. You go, what's the latitude, right? Latitude is the angle from the equator. I'm going to take it to be the angle from the north. Latitude, yeah. Latitude is the angle from the equator. I'm going to just allow it to be angle from the North Pole for simplicity. They differ by 90 degrees. And the other variable is azimuthal angle, which is, let's see, we'll call this one d theta, and the other one d phi. Supposing I take two neighboring points on the sphere, characterized by a d theta, or the interval being characterized by d theta and d phi. There it is. D theta is this much, is this side of a right triangle, and d phi characterizes this side of the triangle. Now, let's suppose for simplicity that this is a unit sphere. That means a sphere of radius 1, just for simplicity. If it's a sphere of radius 1, how far is it? Then theta simply measures distance along the sphere. If I tell you to walk along a line of constant latitude, a line of constant longitude, and I tell you to walk a certain number of degrees or a certain number of radians, then the distance that you walk is absolutely proportional to the angle to the number of radians. Okay? And it doesn't matter where you are, the same number of radians corresponds to the same distance. So, for the unit sphere, the arc distance along the d theta direction is just d theta. That's the distance along d theta. And so we're going to use Pythagoras' theorem, and it tells us that the distance along ds squared is d theta squared. But what about d phi squared? Is d phi the actual distance along the other leg of the triangle here? No. D phi up near the North Pole, a given d phi up near the North Pole, corresponds to a small interval. Down near the equator, the same phi interval is a larger distance. As we go all the ways down to the South Pole, it gets small again. In fact, the horizontal size of the triangle is, let's write it over here, is d phi times sine of theta. When you're up at the North Pole, the sine of theta is very small. Theta is equal to 0 up at the North Pole. It's also equal to 0 down near the South Pole. Theta isn't. Sine of theta is 0 down near the South Pole. This is actually the distance. Sine of theta times d phi is the distance along the horizontal segment here. Then, using Pythagoras' theorem, we would discover that the distance between neighboring points is d theta squared plus sine theta squared d phi squared. This is the metric of a sphere, or a two-dimensional sphere, d theta squared plus sine squared d phi squared. It's the metric in the usual azimuthal and polar coordinates, or the longitude and latitude. What if this were not a sphere of radius 1? What about if it was a sphere of radius r? Then the only difference would be we would multiply the whole thing by r squared. Since this is the square of a distance, it ought to be quadratic in the radius of the sphere. So if we double the size of the sphere, we double every length, and that means the square of this length would get multiplied by 4. So for a sphere of radius r, we've now worked out what the metric tensor is. And the metric tensor would be r squared r squared sine theta squared, sine theta squared, 0, 0. So again, this is not so different from the polar coordinates. Let me just remind you, for the polar coordinates, we had, forget what, dr squared plus r squared d theta squared. Notice they're sort of similar. There's a term which is constant, and then there's a term down here which depends on sine of theta. Somewhat similar. Okay. This metric can never be flattened out. There is no set of coordinates that you can find to coordinatize the sphere so that you make the coefficients of the metric tensor constant. Impossible to do. That's simply because you cannot flatten the sphere onto a plane without stretching it. And so this is a fundamentally curved surface. The fact that it's a curved surface could be detected by creatures moving around on the surface without ever leaving the surface or without ever looking along the surface. For example, they would discover that triangles on the surface have the sum of their angles larger than 180 degrees, and that's because the triangles sort of bow out, making the sum of the angles larger. So a creature would walk as straight as he could along a line, make an angular turn over here, make another angular turn, come back to the same point, and discover that the sum of the angles of his closed triangle would not be 180 degrees. Okay, so that, and therefore would discover that he lived on a curved surface without ever leaving the surface, without ever getting off it and seeing that it was bent in some higher dimensional sense. That's the notion of a metric tensor. That's the notion of distance, or between neighboring points, and it's the notion of curvature, which I'm not going to work out a mathematical expression for curvature. Sufficient for our purposes just to say if a space is curved, you cannot get rid of the variation from point to point in the coefficient of the metric tensor. Same thing is true in space-time. And that was the new ingredient that Einstein introduced into the general theory of relativity. The idea that the proper time between points, first of all, can be represented by a metric tensor which varies in space. Now that in itself is nothing new. Why? Because even if you took ordinary flat space-time and expressed it in funny coordinates, you could make the metric tensor vary from point to point. But the new ingredient was that space-time can be curved. Curved means that there is no way to undo, no better choice of coordinates where you can undo the fact that the metric of space-time varies from point to point. I'm not going to take you deeply into the general theory of relativity. What we're going to do is explore one or two simple geometric situations that come up in cosmology. And I'm not even going to derive, I'm going to simply state what the geometry of various kinds of cosmologies are, and then explore them a little bit and see what kind of world we live in. Now, we're talking about space-time. We're not just talking about space, but space-time. The kind of cosmologies that I'm going to be interested in are cosmologies which are time-dependent, which don't vary from point to point in space. In other words, where every point in space is exactly the same as every other point. That's, of course, not true. If you're in the middle of a star, it's quite different than being somewhere in interstellar space. But on the whole, the universe is homogeneous, which means the same from point to point. Some facts. Let's write down some facts about the universe. On the whole, the universe is homogeneous. Homogeneous does not mean flat. As an example of a geometry which is homogeneous, we have the sphere. The sphere at every point is the same as at every other point. So it's a homogeneous geometry, but it's not a flat geometry. Homogeneous means homogeneous in space, from point to point in space. Not in space-time. Things change with time. The universe grows. So homogeneous in space.
Seems like some points have matter in them and other points are vacuum.
Yeah, but on the whole, meaning on scales larger than the intergalactic separation, things are pretty homogeneous. Right.
So can I pursue that just a little?
What's that?
Can I pursue that
Yeah,
just a little?
sure.
Because this has puzzled me. I mean, I know
Yeah.
about this assumption or how do you, but then you'll see, let's say a Scientific American or something, you'll see some picture that says that the galaxies are strung out and there's these stringy structures.
Yes. You just have to get, that's still small scale structure. That's still small scale structure, yeah. Yeah. Okay, so let's, we can talk about size scales. On scales of a couple of 100 million light years, and remember, the universe is 10 billion light years, the portion of it that can be seen. So on a scale of, 100 million light years, maybe a few 100 million light years, things flatten out. So that's a tenth, so that's a hundredth the size. On a scale of a hundredth of the size of the observable universe, everything becomes rather homogeneous. Now, we look through telescopes and we can see that the universe, all kinds of telescopes, the universe does not seem to come to an end anywhere, it just seems to go on and on. So as far as we know, it's a lot bigger. Not as far as we know that it's a lot bigger than the portion we can see. And so on some sufficiently large scale, it appears to be homogeneous, or largely homogeneous. Now that could change. Some astronomical observation might discover, particularly in the microwave background on the biggest scales in the sky, it might be discovered that there is a little bit of variation across the left hemisphere might look a little different than the right hemisphere. That could happen. This is not a principle of, despite the fact that it's called the cosmological principle, it doesn't mean it's a principle of thought that has to be true. It could change. All right. But at the moment, as far as we can tell, the universe is pretty homogeneous on large enough scales. And we're going to deal with it on large scales. The second fact is that space, not space-time, let's distinguish space and space-time. Space at any given instant, okay, on large enough scales, is flat. What that means is if you take at an instant of time in the expanding universe, you take a triangle, any triangle composed out of the straightest lines that you can make, straight lines, in fact, that the sum of the angles of the triangle add up to 180 degrees, that all the spatial relations at an instant of time are consistent with space being flat. Now yes?
Can you actually talk about large areas of space and all at the same time? That doesn't make sense.
Well, you can talk about small areas of space and it makes sense.
Well, we've been talking about...
No, I know what you're saying. You cannot at an instant of time know anything about 3 points which are separated by a large distance. But you can, let's draw space-time. Here's space-time, time is vertical, space is horizontal. All right, so here's 3 points in space at the same instant of time, 1, 2, and the third one forms some triangle back over here. Okay. So if we happen to look at the world at the same instant of time, there is no way that we can see all 3 points. Okay? But we can collect data later from the 3 points. And by collecting data from the 3 points, we can correlate information about the triangle. And moreover, we can collect it from different perspectives and then bring our signals together and learn a great deal by looking back at this triangle, learn a great deal about what the shape of that triangle was at that instant of time. So it's correct. You cannot know anything. Basically, you can't know about anything except right now, here and now, but you can collect signals. And in fact, I can't know anything about you right at this instant of time. I can only know about you at an instant of time over which light has been able to signal. Same thing true here. So we can look back and correlate data, and that, of course, is what we do. When we look out into the sky and make measurements of galaxies and this, they're all a little bit indirect. But when we make geometric statements, we're making statements about looking back in the sky and deducing what the geometry of space must have been. All right? So the second statement, it's homogeneous everywhere the same. But more than that, space is flat. That's not the same as space-time. Flat is space. Flat is space. Supple is the Lord.
Let's write it backwards.
Huh?
Let's write it backwards up there in our
Flat is space.
Look at it with a mirror.
But it's time dependent. And as time goes on, if you follow 2 points, what does it mean to follow 2 points? Follow 2 galaxies, for example. As time goes on, the distance between those galaxies increases with time. Okay? There's a standard description of such a space-time, one which is expanding as time goes on, but which is homogeneous and which is flat. And it's rather simple. It's easy to understand. At least I hope it's easy to understand. It's described in terms of a space-time metric, a proper time. First of all, it's described in terms of coordinates. So we take the usual coordinates, x, y, and z, and add to it t, x, y, and z, and t. It's just like special relativity, space-time, except the metric tensor is more complicated. In fact, let's see what we can deduce. From the fact that space is everywhere the same and that it's flat, we can deduce that at any given instant of time, we can find coordinates which just allow it to be represented in terms of Cartesian coordinates. All right, so that means that we can expect that it be of the form dx squared plus dy squared plus dz squared, the distance between 2 points. But we should account for the fact, remember incidentally, that in the special theory of relativity, space comes in with a negative sign. So we should really put in here minuses. Just like in special theory of relativity, but we should possibly take into account a question of units. If you were to measure space in centimeters, but ask for the distance between points in meters or kilometers or miles, the only difference would be that you would multiply this by some conversion factor, and let's call that conversion factor a squared. In other words, if we were measuring, let's measure the distance between points by the number of galaxies along a more or less straight line between 2 points. Here we have 2 points in the universe far from each other. There are many galaxies in between. And roughly speaking, the distance between galaxies is all the same, about 2 million light years between neighboring galaxies, okay, roughly speaking. And I'm going to be rough on purpose. And we simply represent the coordinates of these particles by asking how many galaxies are there, galactic spacings are there between them? Well, since the galaxies separate with time, at different times, this measure of distance will correspond to actual different measures in meters. And for that reason, we have to keep track of the fact that our coordinates we may be working in units at a given time, which are not meters, which are not centimeters, but which correspond to a measure corresponding to some number of galaxies between points or whatever. So we throw in a factor. It's simply a conversion factor, a unit conversion factor, from whatever the units of x, y, and z are to actual physical distances, let's say in meters. This a here is constant in space. It doesn't vary from point to point in space. It may vary in time. It might vary in time. For example, if the galaxies are separating, let's call this point x equals 1. Let's call this point x equals 2. It's just the name of the points. This point out here, a little further out, that's x equals minus 1. And we actually make a three-dimensional array, a coordinate patch in space, which expands with the galactic expansion. Right? In other words, we look out, we discover that the galaxies are separating from each other. We imagine some coordinates, which are rectangular Cartesian coordinates, but the coordinate are spreading together with the flow of the galaxies. As the galaxies expand, or as the space expands, the distance between neighboring points in this grid is growing. That's this A of t here. And this A of t does not depend on where you are in space. That's the statement that space is flat. The fact that space is flat means that space can always be represented by a constant set of coefficients. And in fact, those constant set of coefficients can be taken to be of the ordinary Cartesian kind. Okay? That's space. What about time? Time is exactly as it is in the special theory of relativity, dt squared. Dt squared. Let's write it this way. Let me rewrite it. D tau squared is equal to dt squared, same as in special relativity, plus or minus some function of time, which represents the expansion of the universe. It increases with time times the usual dx squared plus dy squared plus dz squared. So this kind of metric represents, here, you can see here's the galaxies. Okay? And we imagine a mesh of coordinates embedded with the galaxies, but as the galaxies expand, the coordinate mesh expands with them. That means that the coordinates that we assign to the galaxies don't change with time. The fact that this is the galaxy at point x equals 1, x equals 0, and y equals 1. This is the galaxy at x equals 5 and y equals 7. That is preserved with time because the coordinate mesh increases with the universe. But we have to account for this expansion. We have to account for the fact that the distance is actually expanding with time, and that's done by a time dependence in the coefficient here. Anybody know what this thing is called, A of t? No. No, it's not a constant. It's called the scale factor. It's called the scale factor, and it's a thing which does not, as I said, depend on space, but it does depend on time, and it represents the fact that any two fixed points in space, fixed meaning to say that they have fixed coordinates, that the distance between them increases in time. This is the basic setup for essentially all of observational cosmology, that the universe is described by a metric which looks like this. All right, so let me tell you a couple of things about...
Can I ask a question here?
Yeah.
I don't know if this is the best time for it, but it's always bothered me. What you talked about is we have two galaxies.
Well,
and
lots of galaxies.
Yeah,
but yeah.
two galaxies, and their metric remains the same.
Well, it's,
The position in space remains the same because the distance between them, between the 2 points changes, but their
right, but okay, that's the
A changes, but the other is not.
Right,
Their position is labeled the
right,
same.
right. The labels, that's right. Think of X's as just labels labeling the points.
But if this is true with galaxies, it's also then true with the meter stick.
No, the meter stick does not expand with the expansion.
But well, that's my point. What's the difference between two galaxies and the end of a meter stick?
The meter stick is held together by molecular bonds. The meter stick is held together by electromagnetic bonds which are strong enough to overcome the expansion of the universe. Right. It's good, very good question. But galaxies are not expanding. See, galaxies are small enough and concentrated enough that their own gravity holds them together. And in fact, even causes them to shrink with time a little bit. Right? A star shrinks with time. The distance between galaxies on the average is large enough that the gravitational interactions between them are fairly negligible. And so they sort of, they expand with the ambient background expansion, but the individual galaxies are small enough that gravity is pulling them together. Okay, so it's an awkward situation where some scales of mass and distance are such that things are being pulled together, and other scales of distance and mass are such that that things are basically just flowing with the flow.
So is that worked out, I mean, in detail? Not by
Sure.
me, but
Yeah,
I mean,
absolutely.
you know,
Absolutely.
that these forces are counterbalancing those, and so there's-
Absolutely. Yeah. No, in great detail.
So I mean, people could
But-
just say, well, the strength of this interaction is this, and the gravitational.
Yep.
Okay.
But in the process of doing that, a discovery was made that things weren't the way people thought. They discovered that there has to be more mass in a galaxy holding it together than the apparent mass that you see through telescopes in the sky by looking at optical light. And that, of course, was the discovery of dark matter. Not dark energy, but dark matter. Right? But once that's accounted for, once you do it once in one galaxy, and do it another time in another galaxy, and you do a whole bunch of cross correlations and checks and so forth, once you've done that, you know that gravity is strong enough within a galaxy to hold it together, not strong enough within neighboring galaxies to keep them from... Now that, of course, there are some exceptions. Our neighboring galaxy, the Andromeda, just happens to be close enough and heavy enough, and we're heavy enough, that the force of attraction of gravity happens to be pulling them, happens to be causing them to fall toward each other. All right? It just happens that those are two unusually massive galaxies at not too large a distance. And so there's sort of an exception in galaxies that are coming together. But on the average, the galaxies are moving apart. And on a scale large enough that gravity is weak enough, they're just all separating from each other. What's that?
There are, in fact, a number of colliding galaxies.
Oh, yeah. Yeah, neighboring galaxies... No, it's not, certainly not an isolated example. But on the average, even neighboring galaxies tend to be moving apart from each other.
Why don't they consider it a force?
A what?
Why don't they consider it a force?
A fourth?
A force. Because it seems that it kind of behaves like a force.
What does?
The scale factor, or the... I guess-
Well, well, let's be precise. I mean, let's be precise. A scale factor is not a force. A scale factor is a scale factor. It has units of a length. It doesn't have units of a force. I mean, I'm not sure what you mean by, say, call it a force. You mean, could it be due to some force that's causing things to...
Because, I mean, it seems that...
Okay, so let's not worry about force for the moment. Later on, we'll come to the effect of gravitational force and how it affects things. But yeah.
Well, it is due to gravity. I mean, it's just a solution to Einstein-Field equations, etc. So it's the thing.
Well,
that
okay,
would become a
let's put
force.
it this way. You see you shoot an object from the surface of the Earth, a cannonball, except very, very fast, 50,000 miles an hour or whatever. Is that fast enough?
Greater than the escape
pretty
velocity.
Greater than the escape velocity. And you see it moving out, moving out, moving out, moving out. Is gravity the thing that's causing it to move out?
No, it's momentum.
It's inertia that's causing it to move out, in a sense. Now, the original shot that shot it out, that is not the statement of inertia, but once it's been shot out by whatever mechanism shot it out, the fact that the Earth and the cannonball are receding from each other is not due to any force. I mean, it's the mistake Aristotle made to think that motion is due to force. It's due to inertia. Okay? On the other hand, really, there's a second thing that's going on. As the cannonball moves out, it decelerates. The force of gravity decelerates it. It may be enough to decelerate it and make it fall back, or it may not be enough to decelerate it and cause it to fall back, depending, but in either case, it decelerates it. The force of gravity causes the velocity to change with time. Of course, asymptotically, if it really does escape, then it keeps going with a uniform velocity approximately. But as it's moving apart, it decelerates. The universe is just like that. There's an expansion, okay? And until recently, it was thought that that expansion is decelerating. The expansion is like shooting an explosion out of a cannon. What keeps it going is not a force. What keeps it going is just inertia. But it was expected that that inertia would be fought by the gravitational attraction between things, not necessarily that it meant that things would fall back in, but that they would be slowly decelerating. So the expansion would be decelerated. That turned out not to be true. But let's say what we can say on the basis of these things. All right, let's talk about the expansion and the distance, the time dependence. Let's take a pair of galaxies. That are separated by a certain distance. Let's take them to be along the x-axis for simplicity. Two galaxies along the x-axis. They don't have to be along the x-axis. I'm just taking it for simplicity along the x-axis. And let's take the separation between them, the coordinate separation, not the actual distance, but the coordinate separation, and call it delta x. Delta x does not change with time. Delta x, remember the coordinates are embedded and expanding. So if this is x equals 1 and this is x equals 5, forever and ever, eternally, from now on, this galaxy is at x equals 1, this galaxy is at x equals 5, delta x is 4. And it will stay that way forever. But let's not specify it, let's just call it delta x. What's the distance, the actual numerical distance in meters, for example, or whatever units we use, between between those 2 points? To find it, we have to multiply by a. A is the conversion factor from these labels, which are simply labels, to actual metrical distances measured in whatever units, whatever physical units we like. I'll talk about meters. I'll use the units meters. All right, so the actual distance is a times delta x, and let's call that d for distance. That's the actual, and a is a function of time. Okay, what's the velocity of recession between those two? How fast are they separating from each other in meters per second? The answer to that is simple. We just differentiate d with respect to time. D is the distance. If we differentiate it with respect to time for these 2 points, then that'll give us the velocity between them. Now delta, that's fixed. Delta is just 4 units in the case of x equals 1 and x equals 5. It never changes. So when we differentiate with respect to time, the only thing that changes is a. The expansion factor is increasing. It has a derivative. And so we can say that the velocity, which is the time derivative, or the speed of expansion between 2 points, is just equal to the time derivative of a. I'm going to use the notation that time derivative is just putting a dot on top of a thing. Time derivative is often, I think we've probably used that before, I hope we have. But if not, dot means d by dt. So this is the time derivative of a times delta x. That's the velocity. Okay. Well, let me do a little trick with this. Let me multiply it and divide it by a. What is delta x times a? That's d, the distance. So I've derived very simply a very simple rule that the velocity of recession between 2 objects is proportional to the distance between them times something which doesn't depend on where you are. It depends on when you are, but not where you are. A dot over a. Remember, a does not depend on position in space. It does depend on time. A dot divided by a. All right? A dot divided by a is the coefficient relating velocity to distance. There's another name for a dot over a? Hubble. The Hubble expansion. Usually, sometimes called the Hubble constant. But it's quite obvious that in general, a dot over a is not a constant in general. It depends on time. A and a dot in general both depend on time. And so the Hubble expansion rate, the thing that's usually called capital H, velocity, is distance times h. But h is nothing but the ratio of the time derivative of a to a itself. Most important fact about it is that it doesn't depend on where you are. It doesn't depend on which pair of galaxies you're talking about. Every pair of galaxies at a particular instant of time will recess from each other, will have a recession or a velocity of separation which is proportional to their distance and multiplied by the Hubble constant, or the Hubble parameter. I think we should call it the Hubble parameter, yeah.
A is dependent upon t. If you have very, very widely separated galaxies, can you use the same t?
At a given instant of time, yes. Right. So, no, you're perfect. What you're asking, I think, is the right question. If you look back and you see a galaxy far enough away, all right, far enough away, and you measure its expansion, should you use a dot over a today, or should you use it then? The answer is then, right? So yeah, but typically a dot over a is changing relatively slowly in time, so that large pieces of the universe, the Hubble constant doesn't change very much with time. But that is taken into account when people look at the recessional velocities, that the recessional velocities have to be slightly modified from this formula to account for the difference of time that you're actually looking at things. So that's a good point.
One more question. It's a question of dimensions in this detail. A squared, A has the dimensions of the length.
Let's use c equals 1, first of all. Let's use c equals 1, first of all, so that time and space have the same dimensions. Yeah. So, yeah. Yeah, no. Think of x's as not having any dimensions at all. They're just labels, they're names. Fred, Charlie, and so forth. X equals 1, x equals 2, x equals 3. Carried, completely dimensionless. Of course, that's somewhat ambiguous. You could choose A to be dimensionless and let x have units of length. That's somewhat arbitrary. I like to think of it as just saying the x's label the points and don't carry any dimensions, and the dimensions of distance are in A. So that's, again, another good point. Okay, this is the Hubble law. Velocity at any given instant of time is proportional to distance with the Hubble constant itself, Is it surprising? No. What it says is the faster you move, the further you get. That's all. Really, that's all it says. The faster you move, the further you get. So if things are moving fast, they'll get further apart. But there's a detailed form that it's called the Hubble law. When you think about it, it really could hardly be any other way. Well, actually, I guess you could contrive, but not with these set of assumptions here. The Hubble law is just very general. In special relativity, light satisfies d tau equals 0. Along a light ray, along the interval of a light ray, dx, dy, dz, dt, and so forth, the proper time is 0. Why is it 0? Let's move along the x-axis. In units in which the speed of light is 1, then dx will equal dt. If the speed of light, of course, if the speed of light is c, then it's dx equals c dt. But if c is set equal to 1, as they are in all my equations, then dx equals dt, and dt squared minus dx squared equals 0. So a light ray is a peculiar path through space-time where the proper time along the path of the light ray is 0. That characterizes the motion of a light ray, that the proper distance along the light ray, or the proper time along the light ray, is 0. Knowing that, and assuming that it's true in the general theory of relativity, which it is, we can read off from this. Let's suppose there's a light ray moving along the x-axis. Forget y and z. Then what is the equation of the light ray? The equation of the light ray is just that d tau equals 0, or that dt equals a of t times dx. We could write that another way. We could divide by a if we liked. Did I do that right? Yes. All right, so a light ray moves with a dx that's not just given by dt, but dt divided by a of t. This makes it look, in the coordinates that we're using, as though a light ray slows down with time. Why? A gets bigger and bigger. This says that the velocity of the light ray, dx by dt, shrinks with time. Now, what's really going on is not that the light ray is slowing down, is that if you go far enough away, things are moving out faster and faster. And so from your perspective, but this is what a light ray does. This is the motion of a light ray in these coordinates, which, remember, these coordinates are not measured in meters. In these coordinates, x simply dimensionless, and the light ray moves an amount of distance dx in a given amount of time. It moves a distance which depends on the scale factor. So you keep track of things in cosmology by remembering that light rays move on what are called null lines. Null lines mean they have 0 proper time, and you can calculate how a light ray would move through the space by knowing that its dx is always equal to dt divided by the scale factor. And the only reason the scale factor is there is because as time goes on, a given dx corresponds to a larger and larger separation. It would be crazy if the light ray always moved with the same dx for a given dt, because at late times, a given dx is a huge, huge distance. So that's taken care of by putting a of t down squares here. So that's the motion of a light ray. And we could calculate, if we knew what a of t is for a particular situation, we could calculate the motion of a light ray. So this is the space-time geometry, a of t, of certainly not the general space-time geometry of general relativity, but it is, on the whole, the fairly general description of almost all versions that I know of large-scale cosmology. Cosmology on a scale large enough that, that you can ignore the variations from point to point. It's more complicated if space were curved. Space could be a sphere. It could be a hyperboloid. It could be something else. Fortunately, space appears really to be flat, the x squared plus dy squared plus dz squared, which makes the formulas rather easy. Okay. The next question, we can ask lots and lots of questions just about this geometry, but the most fundamental question that we might want to ask is, what is a of t? How does it vary with time? How does a of t, does it grow and then shrink? Does it keep growing? Does it grow as a power of time? Does it grow as the logarithm of time? Does it grow if it grows exponentially with time? How does it behave? All right. That is determined by gravitational force and gravitational dynamics. It's roughly the same question, or a version of the question, of if you see a missile moving away from you, how does it move them away from you with time? That depends on its equations of motion. It depends on gravitational dynamics. It depends on F equals ma and all that stuff. So that becomes the next question. How does a of t vary with time? I'm going to work that out for one example. Well, I think maybe we'll work it out for two examples. But
Why is that question any more important than is the charge of electron vary with time, or any physical quantity?
It's not more important than the question of whether the charge of an electron varies with time.
We seem to focus on that question, though. We seem to focus on whether a of t varies with time, though. Whether the universe.
That's because we know that a of t varies with time, and we also are pretty damn sure the charge of the electron doesn't. If the charge of the electron started varying with time and we noticed it, we would consider that awfully important. Right. But from a geometric point of view, from the point of view of the geometry of space-time, not the only question, but a central question would be how a of t varies with time. If a of t didn't vary with time, we would have just plain old flat space-time. We could get rid of this a by changing the units of x. By changing the units of x, we could get rid of this a if it didn't vary with time. Only because it varies with time does the space-time have a non-trivial geometry. It would just be plain old flat space-time if a was constant with time. All right. I did not mean to imply that the variation of a with time is necessarily the most important question of cosmology. But let me tell you, if we discovered a didn't vary with time, we might not change atomic physics very much, and we might not change particle physics very much, but we would sure as hell change cosmology to be something totally unrecognizable from the present perspective. I'm not going to talk about the way that you experimentally detect the recession of velocities and so forth. That's a different topic.
It seems like that always gets brushed over, and that depends on Cepheid variable stars, and that depends on all sorts of physics.
Right.
Okay, it's just too complicated.
Yeah. But before you, but you see, before you can start thinking about actually how you really do measure it, You really have to have some theory behind you to know what it is you're measuring. It's true, you can measure the local velocity of nearby galaxies and so forth without being too sophisticated. But if you want to measure the very, very distant galaxies, then you have to worry, for example, that the Hubble parameter changes with time, as you pointed out. So you better have some basic theoretical structure to begin with before you can even ask the questions, or basic geometric setup. We're talking about the geometric setup and not the way of measuring space-time distances and so forth on astronomical scales. Besides, I suspect most of you have some idea of how astronomy measures distances, velocities, and so forth. Distance, very easy way to measure distances. The easiest way to measure distances is to a distant galaxy is just to look at its luminosity in your telescope. If it's dim, it's far. If it's bright, it's near. And you use a simple law that the luminosity, the apparent luminosity, is like 1 over the square of the distance because light spreads out in a certain way. That's the dumbest and stupidest and probably not the best way to measure distances to distant stars. But roughly speaking, that gives you a pretty good idea of how far distant galaxies are. How do you measure their velocity? You measure their velocity by the redshift of their atomic transitions, by the Doppler shift. And those two together tell you the Hubble law. That's what Hubble did. He didn't get it right numerically. He was off by a factor of 10 or something on his own constant. Incidentally, there's an interesting, supposing the Hubble constant were constant with time, suppose it really were constant and that distances were related by a fixed number h to velocities. Okay? Then you could ask the following question. Run it backward. We take two galaxies a certain distance apart, run it backward, they come together. How long does it take for them to come together? Well, that's easy. You take, let's see, what do? You divide distance. How long does it take? Rate distance. I always have to work this out. Distance equals velocity times time. Yeah. So how long would it take for those two galaxies to collide with each other if you ran it backward? Well, the answer is the distance between them divided by their velocity. If the velocity were uniform, in other words, if the Hubble constant were actually constant, sorry, not if the Hubble constant were constant, if the velocities were constant, if the velocity of this star out here was constant with time and we ran it backward, we could ask how far in time does it take before they collide with each other. I shouldn't have said if the Hubble constant is constant. That was wrong. If the velocity was constant. In other words, if every galaxy was receding with a uniform velocity that didn't change with time, then how long would it take for two galaxies to be on top of each other? The answer would be the distance between them divided by the velocity. But if the velocity is equal to the distance times the Hubble expansion parameter, this reads distance divided by h times distance, or just 1 over h. The inverse of the Hubble expansion parameter is the time that it would take if you ran the galaxies backward for two neighboring or two distant galaxies to be on top of each other. Notice that that time doesn't depend on which galaxies we're talking about. It doesn't depend on how far apart they are right now, because that cancels out. What remains is that the time is equal to 1 over the, so the bigger the Hubble constant, the less time it would take for two, if we ran it backwards, for two galaxies to collide with each other. And it doesn't matter which galaxies you take. Take any pair of galaxies, they'll be sitting on top of each other in a time of order 1 over the Hubble expansion.
But you're thinking of only two galaxies and not the other folks coming in.
Well, of course, if any two of them are on top of each other, they'll all be on top of each other.
So that the model might.
No, sure, might crash. Yeah, but this does give you some estimate of how far back in time before it crashes, before it has to crash. This, incidentally, is no different, really, than saying if I look out and I see something moving away from me with a certain velocity and I know its distance, I can roughly estimate how long in the past it must have been ejected. If I see it moving with a certain velocity and I know it's a certain distance, I can make a good guess about how long ago it was sitting in my lap on the Earth. So it's really no different than that. It's a crude and rough estimate of how long ago the Big Bang was by measuring the velocity of distant galaxies. Measuring their distance, we get the Hubble parameter. The inverse of the Hubble parameter is, we can call it the age of the universe. It's one measure of the age of the universe. Nobody knows when the universe began and how it began, but this inverse h is of order the time to the Big Bang. Would you incidentally expect, what would you expect? Would you expect the real time was shorter than that or longer than that?
Long.
Why?
Because there might be other forces.
Well, we haven't even mentioned forces here. This is what would happen if the velocity was absolutely uniform. So, okay, so think about that object that's moving away from us. We measure its velocity sometime in the future. We see it's moving away from us with a certain speed, and we want to know how long ago it left the Earth. Well, we can answer that question by running it backward. Take that same object, reverse its velocity, and ask how long it takes to fall into the Earth. The answer is less time than if it were moving with uniform velocity, because the Earth attracts it and causes it to accelerate toward the Earth. It takes less time. So this, in the standard old-fashioned kind of cosmologies, this estimate of the age of the universe was a little bit too long. The universe would have to be less old than that. But not by a lot. Not by a lot.
But did you tell us that within our own galaxy there's no expansion going on?
Right.
So when you get to galaxy links,
Oh,
then
well, no, right. At some point, this theory has to crash. Crash means exactly what? As you run backward, or really the backwards of what happened as you went forward, the galaxy sort of materialized out of fluctuations and a relative degree of almost complete homogeneity by attracting the matter attracting and clumping and so forth. And I don't think you would, that is not what you would see if you literally ran it backwards. If you run a real event backward, you don't get to see the backwards of the forward motion. If you, yeah, right. I mean, there's various ways to describe it. Sometimes it's called the second law of thermodynamics. Sometimes it's called the increase of entropy. Sometimes it's just called shit happens. And, right.
When we measure the distance to galaxies, clearly we're measuring in terms of some standard lengths that we have here on Earth. So we'll compare
Yes.
that distance.
Yes.
Well,
Yes.
so is there a physical experiment that allows us to distinguish whether these galaxies are expanding or that A
Whether
of
the
T-
galaxies themselves are expanding?
No, whether the A of T is growing,
Yeah.
I should say, or whether my ruler is shrinking.
No, there's no way to tell the difference.
So there's a sort of equivalence principle of scale.
Yeah,
We don't-
only ratios of lengths are really important in physics. Only ratios of dimensional quantities. So what you can say is that I think that is a very good point, and we should talk about that. The distance between galaxies divided by the length of a meter stick is increasing. And that's really all you can say. Yeah. or equivalently, the meter stick is decreasing. Yeah. And you take your choice. But it's standard. I mean, it's a matter of convention, but we like to think that the parameters of atomic physics and molecular physics and all these things which hold meter sticks together is fixed. We like to imagine that the mass of the electron is fixed, and all these fundamental parameters are fixed numbers. The speed of light, but in particular dimensional numbers. I would not like, I can do it. I can say the radius of a proton decreases with time, instead of saying the universe expands. It is a matter of taste more than anything else, and a matter of historical preference, a matter of historical convention, that we tend to think of the microscopic atomic distances as fixed things. And they, of course, determine what is a meter stick, incidentally. Why is a meter stick a meter long? Well, what is a meter? A meter is a distance from your nose to your arm. Why is it so big in atomic units? Because it takes a lot of atoms to make an arm. Okay? So it's a matter of biology. But that biology, we like to imagine, doesn't change with time, and so we use conventions which say that the size of an atom, the size of a proton, and so forth, is determined by a fixed set of parameters that enshrined in somewhere in Paris. I don't know where they keep the meter stick these days, and finished. We use those units. With that convention, the universe is expanding. If somebody big enough who looks at the universe from a large distance perspective and likes to use the distance between galaxies as a basic unit, that observer will see everything shrinking and shrinking, and will say atoms get smaller. So it is a matter of taste.
The question is that the only form of the metric that follows from flat and homogeneous?
Apart from coordinate transformations. Now, this is the metric in some specific set of coordinates. In other words, the right statement is that the metric, given these two things, the metric can be brought to this form by an appropriate choice of coordinates. Yeah. Yeah. So that's in a sense a derivation that I didn't do, but it's not terribly hard. Yeah.
Since we were talking about running the tape backwards, if distance between 2 points was 0, then the velocity would also be 0, which means there would not be...
No, I'm saying supposing we look at everything today. We measure what the Hubble constant is today. Okay? Today, and then we run it backward. If we run it backward with today's parameters, that will tell us how long it takes for the universe to collapse into something much smaller. The Hubble constant, of course, varies with time. It varies with time, and in fact, it tends to increase as you go back toward the Big Bang. The Hubble constant was much larger at the earlier times than it is today, so, and the velocities were much larger. So even though the distance between two galaxies may have been much smaller, the velocities of ejection of those same galaxies was larger in the past. That means that the Hubble parameter must have been much larger in the past. Okay. But what I'm saying is, supposing we look at things today, we look at things through our telescopes, we measure today's Hubble constant, we know what it is, that tells us today what the ratio of distance to velocity is, and then assuming that the velocity is uniform and it doesn't change with time, we can ask how long it would have taken for a collision. All right? Then we add to that a little bit of information from gravity that if we did run it backward, then we would be overestimating the time, because the gravitational attraction would cause things to speed up. So, and one can do this with great precision, so we know what the age of the universe meaning the time until, let's say, galaxies would have been sitting on top of each other, it's 13.5 billion years. Let's proceed a little bit. How do we find out what A is doing with time? Well, one way, of course, is to measure it. And you can look back through telescopes into the very, very distant past. You can look at, in principle, you can look at two galaxies. You could, in principle, try to, in fact, you don't do it this way, but you could look at them carefully enough to see that they're receding from each other a little bit. This was long, long in the past. And so in that way, you could measure the relationship between their velocity and their distance long in the past, and determine how the Hubble parameter changes with time. And if you know that, you can also figure out how the scale factor changes with time. Of course, that's not the way it's done. The way that it's actually done, well, is more sophisticated than that. But the first thing is, what should you expect? What should you expect on the basis of basic Newtonian physics of gravity? Right? The answer is roughly analogous to the same question that you would ask about the outgoing cannonball. How does the distance of the cannonball, remember what A is now, A is just the distance between a pair of nearby galaxies. How does it vary with time? It varies with time in a manner which is entirely analogous to the way the bowling ball, not the bowling ball, the cannonball distance would recede from the Earth. What governs that? Newton's equations governing forces and acceleration determine how the cannonball would recede from the Earth. And so the exercise of figuring out how A varies with time is a simple exercise in Newtonian physics, in Newtonian F equals ma type physics. And I'm going to show you how it works in a simple example. Let's draw all the galaxies. Here they are. Well, that's not all of them. In an approximation where the universe is very big and the distance between galaxies is small and everything is homogeneous and uniform, we can think of the galaxies as sort of being smeared over space in a very homogeneous gas, a sort of gas of particles. The gas of particles are more or less standing still, they're not standing still relative to each other, but they're flowing with the flow, and the gas of particles is expanding. Let's say this is us over here. Now, there's no reason why we should be concentrating on us, and we'll discover in the end that the equations don't depend on who us is, whether it's us over here or somebody 5 billion light years away. The equations for how the universe expands should not depend on who we choose to be us, but let's choose us anyway. Here's us over here. And now let's take some galaxy at point X. Let's put it on the x-axis. Let's put it on the x-axis. We are at x equals 0 by definition. Here's a galaxy at point X. X is its label. Its distance is a times x. So its distance, the distance here, the actual distance in meters is a times x. Here we are over here. And let's solve Newton's equations for how this galaxy moves. What are the forces on the galaxy, on this galaxy, this red galaxy over here? Well, there is, of course, the force of attraction to our galaxy, but that's not all. There's a lot of other galaxies here in between. This is forming a gas. All of these galaxies, and there's also galaxies way out here. All of these galaxies gravitationally attract the galaxy that I've called X. Okay? So it sounds like a very, very hard problem to calculate the motion of X. But Newton would not have found it a hard problem. I don't know, I don't think he set up this exact problem, but he would not have found it hard. He would have used a fact that he discovered about gravitational forces. It's basically a fact about inverse square forces. Here's the statement. If you have a spherically symmetric distribution of matter, spherically symmetric about the origin here, And the uniform distribution of galaxies is spherically symmetric. It means it's the same in every direction. Then the net force on an object is the force due to all of the matter inside the sphere about the center. In other words, the net force pulling this galaxy toward the center of coordinates, us, is due to all of the matter inside the sphere, and all of the matter outside the sphere doesn't contribute anything. That's one statement. So, in calculating how x moves, you can forget all the material on the outside. Just doesn't make any difference. On the other hand, Newton also discovered something else. He discovered that if you have a spherically symmetric distribution of mass like this, then the force on an object due to the spherically symmetric mass distribution on the inside of the sphere is exactly the same as if all the mass were concentrated right at the center. So this means all we have to do to find out how a galaxy at distance x moves, is to study its motion in a fictitious problem where all of the material within a sphere bounded by x, all the things closer than x, are all concentrated right at us. And then just pretend there was a problem in which a cannonball was ejected from the Earth. And that will give us the exact correct answer. That's the thing that Newton would have known, and I'm sure if he didn't solve that problem, he would have solved that problem very easily. So let's work it out. Well, I don't know, maybe we should quit now. I think we'll work it out next time. We'll work out in detail the equation of motion for how A increases with time, and work out the simplest cosmology, what's called matter-dominated cosmology, find out how A increases, and discover one of the basic laws of cosmology that we'll talk about next time. Are there questions now? Because we'll do one more class, we'll finish this up, and that'll be it for the summer. No questions? Yeah.
Probably too much to answer in a couple of minutes, but let me at least ask it.
Oh.
We look way out into the universe and we see light was emitted 12, 13 billion years ago. But 12 or 13 billion years ago, the universe was very small. So why aren't we seeing that light very close to us instead of very far away from us?
The universe, things were much closer to us. It's this equation for the light ray here. Let's see. What are you asking me? The light that we see. I'm not sure how to describe this.
The second part of the question was not clear.
Say it again?
The second part of the question was not clear.
We look way out into the universe and we see light that was emitted 12, 13 billion years ago.
Right.
Okay. And it's been coming at us for 12 or 13 billion years.
No, it's been coming at us for 12 or 13 billion years.
But 12 or 13 billion years ago, the universe was much smaller. So how can this light appear to be from so far away?
Well, okay, so we have to work out how a light ray moves. I'll do that next time. I'm tired now. I'm reaching my exhaustion point. Let's work out next time exactly how that works.
And it may be the same question, but observe the universe. If the universe started from the Big Bang and expanded, in the early days it was expanding much slower than the speed of light, how is it that anything in the universe is not observable to us? It was all very compact and not expanding fast.
Well, okay, so let's, yeah, it is the same question. Let's plot some light rays. Here's T, here's X. Okay. Now, what happens to the scale factor very early in time is that it gets very small. In fact, let's just assume it goes to 0 in some simple way. Okay? And let's plot what a light ray looks like. When A is very, very small, the dx by dt is very, very large. So the light ray, let's say the light ray starting from this point over here, this is t equals 0, and at t equals 0, A is also very, very small, essentially 0. Okay, so the light ray starts out very fast, measured in x, because A is very small. And if A is small, then the distance that it goes in a given interval of time is very large. So it starts moving very fast. Let's see, that means, fast means almost horizontal. An infinite speed would mean completely horizontal. All right? Then as A starts to grow, I'll call this the coordinate velocity. It's not the ordinary velocity, but the coordinate velocity of the light begins to slow down, and the light slows down according to some law that depends on how A varies with time. Okay? Now here we are right over here. Here we are, and here's today. Space is flat, goes on and on forever and ever. No matter what this curve is shaped like, if we displace it over to here and run it backward, we will come to some point. We'll come to some point. That's the point which sends light to us from t equals 0 that gets to us now. That's it. The light that we see came from this point. I don't know what else to say about it, except that we run this curve backward. Remember, it's apparently slowing down, slowing down, slowing down. And so wherever we start, we can run it backward, and it will eventually intersect t equals 0. I don't know what else to say. I mean, except to work out some examples of how light propagates. So there will be some place that the light originated at. We'll work out an example with a specific A of t, and we'll try to calculate how far away that light originated from and how long it took to get to us. I'm running out of steam, so I don't want to try to do it now, but we can do it. Yeah.
So when this Big Bang event happens, and how come, I guess, matter didn't all expand at the same rate so that everything should be organized in like a ring?
No, it didn't blow up from a point. Everything started out completely homogeneous. It started out completely uniform, but extremely dense. The tabletop here went on and on forever. Now, that's probably not really true, but just imagine it. The tabletop is extremely big, but extremely dense. So that molecules, let's think of them as molecules, but molecules that we see today as being 10 billion light years away from us are really 10 to the minus 10th centimeters close to us. Everything that's in today's observable universe was all in a tiny, tiny patch here. Okay? And then the whole tabletop started to expand. Okay? There's no shell that formed. There's no sense in which some matter was ejected from a point and then went out and formed a shell. Just everything started to uniformly expand. And so it continued to form a completely homogeneous space, but the separation between points just got bigger and bigger. Think of a balloon. Think of a balloon expanding. You start with the balloon is small, and it's got a lot of dots in it. And then it expands, the same dots are further apart. But the balloon is uniformly filled with dots. It's not that if this is our dot over here, we see dots on some shell far away. The entire balloon is uniformly filled. That's the nature of the geometry we're talking about. Homogeneous, everywhere the same, but uniformly expanding.
So there's no assumption in that the universe is finite at that time.
No.
So, I mean,
No. Well,
it's
the
not a
universe
point,
is finite,
it's
but
not
it's
a
like
point blowing up.
Hmm?
It's not necessarily a point blowing up.
No,
You have
no.
infinite expanse, you could have infinite expanse at that point, at that time. That all goes boom.
But some things
So
were
it's
not,
not that.
but some things were not affected because the fact that you're keeping, that you can actually measure, the fact that, you know, you can see that there's this scale factor and things increasing, means you're assuming that your ruler isn't changing.
Yes.
Because obviously there's something that's not varying or varying at the same rate.
As
So,
what?
As the expansion of the universe.
You answered that earlier in the same attraction, gravitational attraction.
But how come the gravitational attraction, that force, wasn't affected by this expansion event? Or I guess that's just the way it,
Why the force wasn't, well, the force from the force between a galaxy and our galaxy is affected by the expansion. The closer it is, the stronger the force. But we want to work out the consequences of that. When this sphere was much smaller, remember now, only the things within the sphere affect the motion of this X relative to us. Okay? When all of this was much smaller, so that same galaxy was right over here, there was a much larger force on it.
but you would consider gravity or the other forces to actually have the same strength during, when everything was closer together.
Yeah, the universal gravitational constant did not change over time.
The gravitational constant did not change, but the distance between us and other things did change, and so the force depends on constant and also distance.
Is the universe, is expansion as double curvature?
Well, say it again.
The expansion, is the universe expanding in curvature? Does that curvature is the expansion? Or is it just flat like space?
Okay, the observational evidence. Okay, let's begin with the Earth. Is the Earth curved or is the Earth flat? All right? If you go out on a large plain, the schoolyard, and you try to look around, you can't tell if the Earth is curved or flat. Why? Because you're not sampling a large enough portion of it to tell. Yeah, that's right. Your triangles will not you will not be able to tell. The only way you can tell is to sample a large enough portion of the Earth so that you can actually see its curvature. Right? The same is true with the universe. If you only get to sample a portion small by comparison with the radius of curvature, the operating term here is the radius of curvature, and for the Earth, the radius of curvature is just its radius. Unless you can sample a part of the Earth that's comparable to the radius of the Earth, you will not see that it's curved, particularly if you're a little bug moving around on the surface of the Earth. Okay? You have to explore a region which is more or less of some finite fraction of the entire radius of the Earth in order to observe the fact that it's curved. The same is true of the universe. You have to explore a portion of the universe which is comparable, not necessarily comparable to, but at least some reasonably large fraction of the radius of curvature of space. Space may also be curved. If you explore too small a fraction of it, you can't detect the curvature. All right, so the statement is today, what you might be able to do, for example, is you could come back to the Earth. You might be able to put limits on how big the Earth is by exploring some triangles out on the football field, assuming the football field was nice and flat. You could put some bounds on how big the Earth is. You could, by measuring the angles of triangles and so forth, you would find that it's very close to being flat. And you would say, well, the deviation from 180 degrees is less than 0.0001 radians, and therefore the Earth has to be bigger than a certain size. Okay? Otherwise, you would have seen the funniness of triangles. Same thing you can do by exploring a region of space of size billions of years, measure triangles at various astronomical ways, measure very, very large triangles, compute the angles and so forth, and ask whether on the scale that you're measuring there's any visible curvature. The answer is no. On the scale that we've measured up till now, we cannot detect the presence of curvature of the universe. It appears to be flat on a scale of 10, 20 billion light years. The meaning of that is the same as it is for the Earth. It means that if the universe is curved, its radius of curvature is much bigger than the visible portion. How much is much bigger? 10 times bigger, at least, at minimum. Maybe much more than that, but at absolute minimum, the universe is 10 times larger in radius than the portion that we can see. And so that means that we can't really detect the curvature very easily. Is it really curved? It might be. Now what happens if it is curved? It starts out very curved, so the curvature is large if it's curved. A small sphere is highly curved. As the sphere expands, the curvature gets smaller and smaller, until when the sphere is as big as the Earth, we can barely see the curvature. So the numerical measure of curvature on the surface of the Earth decreases as the Earth gets bigger and bigger. The same thing is true of the universe. The curvature of the universe decreases as the universe expands, and apparently the universe has expanded so much that even if it were a curved ball to begin with, it's expanded to the point where we can no longer detect its curvature.
The reason I asked you that question is, if it has curvature, then curvature should have two components. One is expanding, the other is contracting, right? By its nature, by its geometric nature.
Look.
So the universe, in the meantime, must be contracting.
Sorry.
It's expanding.
Wait. The universe is known to be expanding.
Expanding, yeah. But if it has curvature, then there is a component to it that's contracting also.
No. I mean, the expansion or contraction of the universe is controlled by this A of t. The universe could be flat, it could be positively curved, it could be negatively curved. Whether it's expanding or contracting is not determined by that, it's determined by how A of t evolves. If A of t continues to grow, it's expanding. If it grows and recontracts, then it recontracts after a while. If it's contracting, then the universe is shrinking. There is a connection, which is no longer apparently believed to be true, but there was an old connection between the curvature of the universe and whether it's going to recollapse again. That has changed, and I will tell you about it next time, but I don't know. Expanding is expanding, contracting is contracting. I wouldn't say there's a component which is contracting, and that's not the way I think about it. I don't know how to think about it so that expansion and contraction coexist. Contraction could follow expansion in the same way that a ball thrown into the air which is receding could fall back down. That's essentially the question. Is this particle here moving away fast enough that all of the mass within this sphere is insufficient to pull it back down, in which case it will escape, or is it moving slow enough so that the mass within here will pull it back down, in which case the universe will crash, okay? Or is it just in between on the knife edge? It appears to be just in between on the knife edge, between basically right at the escape velocity. Okay, let's
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.